So now what I will get from here, so as this integral is valid for any arbitrary volume, that means, so this is my integrand, okay, and this is the integral. So if it is 0, then the integrand must be 0. That means from here I can directly write that dou rho by dou t plus divergence of rho into v is equals to 0. This is the continuity equation, you know, right? Am I right? Okay, so this is the continuity equation. So do you know what is the difference between an incompressible flow and a so what is the incompressible flow? So for an incompressible flow, what will be the form of the continuity equation? So if I keep the density constant is not the incompressible flow. Okay, you have to keep in mind. So that's what I am saying it. So if you take the rho equal to constant, so what is the, this quantity will look like? It will be simply divergence of v equal to 0. Okay, but this incompressible flow is different from the density constant flow. Okay, the incompressible flow means that the overall what should I say, the volume is somehow that volume is deforming, but the net volume is constant. So it will also the same case. So for an incompressible flow, divergence of the velocity will be equal to 0. This is for incompressible flow, you need to keep in mind. Though these two equations are different for rho constant and for the incompressible flow, but still it has some difference. Okay, because in the first case, in the second case, your entire volume is also constant. So do you want me to solve some problem? Okay, let me see if I have some problem from the. Okay, when is your last date of submitting assignment for this week? Hmm? 10th August. Okay, so let me solve just one small question from here. So let's say you have a velocity field where your v in the Cartesian coordinate system, v equal to u I cap plus v j cap plus w k cap, in the Cartesian frame of reference. So let's say this, you have u direction velocity is equals to b y square. Okay, you have the v direction velocity by a x square, and you have w direction velocity by c x square y square. Okay, that means u, v and w are given, and a, b, c are constant. Okay, so if this flow satisfy the continuity equation, then what is the relation between A, B and C? Can someone try to solve it? So what is my criteria for a incompressible, for satisfy the continuity equation? In this case the density is constant for a steady incompressible flow. So for an incompressible flow, the continuity equation is this. So that means it is, if I expand it, it will be dou x of u, like dou u dou x plus dou v dou y plus dou w dou z is equal to 0. Okay, this is the continuity equation form. Now what is the derivative of u with respect to x? Is 0. What is the derivative of v with respect to y? That is also 0. Okay, because there is no y term. What is the derivative of w with respect to this? This is equal to 0. So that means the left hand side is already 0. Sorry, the left hand side is already always 0. So that means it will satisfy the continuity equation for any arbitrary A, B and C. Okay, for this case. Now you have a small task to do, that you have to, so I derived the continuity equation from this RTT. Okay, from this Reynolds transport theorem I have derived the continuity equation. You try to derive from yourself. Okay, what will be the momentum conservation equation from here using RTT? What will be the momentum conservation equation? That you try to derive from yourself. If you face any problem, you tell me in the next Saturday. I will definitely help you. But for the sake of for the time constant as it is there, I'll just simply write the momentum conservation equation in the differential form. Okay, which is the Navier-Stokes equations. All of you definitely know that. So let me write Navier-Stokes equation for an incompressible homogeneous isotropic fluid. Like what I mean by what I mean by incompressible homogeneous isotropic fluid, that you will know all these things if you derive from yourself by using some textbook or something. If you do that, you will get that idea. While deriving, you need to consider all those assumptions, that it is a homogeneous, the fluid is homogeneous, or rather you have to consider that the fluid is isotropic. Isotropic means that the properties are invariant about the axis. Okay, that is mean by the isotropic fluid. And for an incompressible, as you said, that divergence of V is equals to 0. So if I write the vector form of it, it will be simply, so you know the tensor? No, I don't think you know, right? You don't know, right? Okay. So the vector form of it is equals to, looks like this: dou V dou t plus V dot del, where del is the nabla gradient operator. Okay, is equal to, so you can multiply the rho in this side, this is rho into this entire term, is equals to minus gradient of P, where P is the pressure, plus mu into Laplacian of V, okay, plus you have body force term. So this is for unit volume, right? Yeah. So this is per unit volume. So this is body force per unit volume. This B is the body force. You can write it in terms of unit mass also. So in that case, it will be dou V dou T plus V dot del is equal to minus 1 by rho gradient of P plus mu by rho is the dynamic viscosity, rho is the density, and mu divided by rho is the kinematic viscosity. That I guess you know. Plus this is, let's say, some B. So this B is the body force per unit mass. Okay. Okay. So can you write it down? Like from this, it is very easy to write it down in the x direction momentum equation, y direction momentum equation, and the z direction momentum equation. That's not a hard thing to do. Okay, for the sake of your clarity, let me write it down. So that means if you put that, of course I am writing everything in the Cartesian coordinate system. Okay, I am not using cylindrical or the spherical or any other coordinate system. I am simply using the Cartesian coordinate system so far. So this V is equals to u I cap plus V j cap plus W k cap. Okay, and this P is a scalar, and this, let's say, B, the body force term, have Bx I cap plus By j cap plus Bz k cap. If you put these two into this, and what is this nabla? All of you know, it is dou x of I plus dou y of j plus dou z of k. Okay, if you put this term into this, then you will get the you will get the momentum equations in x, y, and z directions. Separately you can get it. So what will be the x momentum equation? That means the momentum equation along x direction. So x momentum equation will be dou u by dou t plus u dou x plus v dou u dou y plus w dou u dou z will be equal to minus 1 by rho dou p dou x plus nu into simply Laplacian of u. So what is Laplacian? Laplacian is equal to this. Okay, plus Laplacian of u plus bx. Okay, what will be the y momentum equation? This y momentum equation will be dou v dou t plus u dou v dou x plus v dou v dou y plus w dou v dou z. What will be the right hand side? Minus 1 by rho dou p dou y plus nu Laplacian of v plus vy. Okay, and what will be the z momentum equation? The z momentum equation will be dou w by dou t plus u dou w dou x plus v dou w dou y plus w dou w dou z will be equal to minus 1 by rho dou p dou z plus nu into Laplacian of w plus bz. Okay, so these are the x momentum and the y x y and z momentum equations which we will use later for solving different problems. But before going into that, this term, the rho into this term is basically the convective term. Okay, or this is known as the convective acceleration. Okay, this is the temporal terms. This term is temporal term. This is the convective term. This is the pressure gradient term. This is the diffusion term. Okay, and this is the body force term. And this entire left hand side is called the material derivatives. Okay, that means I can write later that the d dt, capital D dt, stands for the material derivative. So what is this? This material derivative is simply, you can write it as like dou v dou t plus this v, if I call it as v dot del. Okay, so what is dou u by dou t material derivative? It will be simply dou u by dou t, like du by dt, into u dou u dou x plus v dou u dou y plus w dou u dou z. Okay, so this is the material derivative term. This entire left hand side is basically the acceleration term, the fluid acceleration term, if you consider in that sense. In the right hand side, this dou p term, so this is the acceleration term, fluid acceleration. This is the pressure gradient term, this term. This is the like the diffusion term. This is the viscous stress and all these things are involved here, and this is the external body force term. Okay, so using this, now let me write it down, that equation once again, because I will try to derive, like try to tell you at least in word how you can see the difference like the different equation. Okay, if you mind, if I write it down in tensorial notation. Anyone know the tensors? Anyone know tensor, like the Cartesian tensor algebra? Okay, then I will stick to vectors only, not in tensor. Fine. So let's see. So what is my equation? My equation is the NS equation, or the Navier-Stokes equation. in vectorial in vector form looks like this. So I have dou v dou t plus v into del nabla gradient operator is equal to minus 1 by rho gradient of p plus nu is the kinematic viscosity plus nu is the kinematic viscosity into Laplacian of v plus b. So as I said that this is my inertial term or the acceleration of the fluid. Okay, this is the pressure gradient term, this is the diffusion term that is associated with the viscosity of the fluid, rather the kinematic viscosity, and this is the body force term. Okay, so this is acceleration term, this is pressure gradient term, this is diffusion term, where it is related to the viscosity of the fluid and the viscous stresses and all these things will come. This is the diffusion term and this is the body force per unit mass, definitely. Okay, per unit mass. Okay, so what will be this equation if I consider a static fluid? So for a static fluid, that is the fluid static if you talk about, so for fluid static the velocity is 0, definitely the velocity is 0 because the fluid is stationary. So if the velocity is 0, then what will be the fluid static equation for fluid static? That means this right hand side is entirely 0, there is no acceleration of the fluid. Okay, the diffusion term will also be 0 because it will not feel any viscous stresses, the fluid will not feel any effect of viscosity, will be not felt by the fluid. Okay, if the fluid is in static form, that means this diffusion term is also 0. So what is the equation for the fluid static? For the fluid static you can simply write that B, the body force, that means minus 1 by rho gradient of P is equal to B. This is the equation for fluid static. Okay, so you can write it in a Cartesian form also. If you put that B is equal to Bx plus By plus Bz, then what will be the Cartesian form of this? It's very simple. Okay, so it will be if you write it down, it will be dou p dou x will be equal to minus rho bx, dou p dou y will be equal to minus rho by, and dou p dou z will be equal to minus rho bz. Okay, if you consider the gravity or something, then only the z component will be there. This bz will be simply z. Okay, for if you consider only the gravitational acceleration or the effect of gravity as the body force, then this bz will be z and bx by will be 0. That you solved in, I think, in different problems also previously. What about the incompressible inviscid flow? Okay, or the rather I should say it as the Euler equation. What if we have the capillary action, you are saying, like the capillary action for the okay, capillary actions in the fluid static, you are saying, right? So for that capillary actions which you are talking about, for that also, so it's kind of the interface flow you are talking about, that the entire fluid as at rest, but when there will be a capillary effect, the fluid will have some movement, and when the fluid will have some movement because of the capillarity, you can't no longer use the fluid static equation. For that interface, like the interfacial flow or something, you have to use the like the dynamic equation, the Navier-Stokes equation. Okay, if there is some flow because of the capillarity or some other physics, you have to use the incompressible the Navier-Stokes equation. You can't use the fluid static equation, because in that case the fluid is not at rest, at least in that portion where the capillarity effect is more prominent or where some other effect is more prominent. Okay. Okay. Do you want to write something, like which page, you tell me? I'm scrolling it down. Okay. Here. Like, what is the question you have? Okay, so I will talk about the Euler equation. So for Euler equation, like I can directly get it from the Navier-Stokes equation itself. So for the Euler equation, this acceleration, the fluid is not at rest, this acceleration term is there. Okay, pressure gradient term is also there, but there is no effect of fluid friction, or there is no effect of viscosity. Okay, this is a hypothetical situation of, like, it's not entirely hypothetical, but you are just ignoring the effect of viscosity of the fluid. That means if you ignore this term, that is nu into Laplacian of v, this term you are setting it as 0 for this Euler's equation. Okay, this term is 0. So that means what will be the Euler's equation? It will be simply dou v dou t plus v into del equal to minus 1 by rho grad p plus v. There is no effect of viscosity. It's only the body, like the body force term is there, and the pressure gradient term is there, and the acceleration of the fluid or the inertial term is there. Okay, and this is the full Navier-Stokes equation. So in the same way you can write this equation in x, y and z direction, and from there this Euler's equation you can actually derive the Bernoulli's equation, which I will do in the next class. You can do like the Bernoulli's equation, which you know, that is not the like the full form of the Bernoulli's equation, that you know that there is like the total mechanical energy is conserved. That is not the actual expression for the Bernoulli's equation. That is of course the energy conservation equation, but we will derive formally the full form of the Bernoulli's equation, which is not an easy task to do. That we will see in the next class, okay, or in the next live session we will talk about that. So far if you have any questions, you can go ahead and ask. Anyway, I will share this PDF with you, so you don't need to take screenshot and all. I'll just share it. Okay, you will get it, I guess. So do you have any other question? And for the assignment problem, because your submission date is on 10th August, so I can't like solve these assignment questions now. Okay, so for the assignment questions, if you have any doubt, just remind me on after 10th August. Okay, if you have any other question, please go ahead and ask. Body force term is associated with particle. Yeah, like when in the later classes we will talk about particles and all, like the particles in a flow or particles in fluid. That time the particle will experience some body force, just like the gravity or some electrostatic force or some magnetic force. Anything is possible. But at the same time, the body force is also applicable for the fluid body also. Let's say a column of liquid, it like the gravity is always acting on that, right? So that gravity force is a body force that is also acting on the fluid as well. But when there will be two phase, like you have the fluid phase and the particle phase, there the body force will applicable both for the fluid and the particle. So it is not like that it is only associated with the particle, not with the fluid. It is not like that. It is associated both with the fluid as well as the particle. Yes, here it is for the fluid, not for the particle, because I have not introduced any particles in the discussion so far, which I think we will do from lecture 7 or something, where the particles will come into the picture. So okay then, thank you. We will the next week at this time we will again meet. If you have any doubt in between, I think in the next week 2 he will discuss about the Bernoulli's equation, the Navier-Stokes equations in cylindrical coordinate, and I think what else is there, let me check it once. Yeah, in cylindrical coordinate, the continuity equation and the solution of Navier-Stokes equation, where it is possible to solve